and evaluate that expression for the case when tau is equal to 0. Since we are interested in the expression of gamma 1, 2 for tau equals 0. So this is equal to time average of V1 conjugate complex times V2 times T divided by I. So you see I need a drawing here. So we will assume now that the extended source we are looking at here, so which is very distant, out of the blackboard, of course, is composed of many small infinitesimal surface elements that you see projected on the sky, where their number goes from 1 to big N. So the visible surface is just integration of all these small surface elements. And what we may write is that, of course, at point P1, the electric field is just a contribution of the electric fields due to all these infinitesimally small surface elements. So I may write that V1 of t is summation from 1 to n of Vi1, where Vi1 means that contribution of the surface element I at the point 1. It's the same for the second hole. And what we do now, where we just insert this expression in that one, and V2 in that one. And then, we will have a series of cross products, many cross products. And what we obtain is the following. We have a series of a summation on just one index, Vi1, Vi2. So it's one surface element contributing to the hole 1 and hole 2. We are looking at the correlations. And then we have all the contributions, due to surface elements which are distinct, Ij, contributing at point 1 or 2. Well, because the source elements are emitting light in an incoherent way, so there is no possible interference between the light emitted by two different surface elements, Well, on average, this summation is just equal to 0, because it's just random numbers, So what remains is the other summation. So the summation from I equal 1 to n, the time average of Vi1 star t time Vi2 of t divided by I. Okay, now do you agree that Vi1 or wait, what I will write now, just a reminder of this expression for the small surface elements. So I don't write it down on the blackboard. For an incoherent light source, I said the second summation appearing here is obviously equal to 0. And the contributions Vij can be expressed as, well, this is essentially this expression, but where I've taken into account the effect of the dilution, geometrical dilution, because there is a distance between the source element and where you are, and we know that the intensity varies as the inverse of the square of the distance, so it means that the amplitude varies as the inverse of the distance. And this is the reason why you see here a division by Ri1, which is the distance between the surface element I and the hole number 1. Okay, now if I would like to evaluate what the value of this product, I make use of those relations and I find that it's equal to, so after we'll take the time average, it will be contribution, this is the real amplitude due to the surface element I, taken at the time t minus Ri1 over c. This is the propagation time, correction for propagation time from source element I to the hole number 1. divided by R I1 to count for the geometric dilution effect, multiply by, so here I conjugate complex, exponentiation of minus I2 pi nu multiplied by T minus R I1 over C. Now multiply by AI T minus R I2 over C divided by R I2. Now the first thing I will do is the following. So this is the distance from surface element I to hole 1, and this is the distance from surface element I to hole 2. Would you agree that I can do that or not? It is as if I would be dividing by, okay, maybe 10,000 light years and 10,000 light years plus 1 centimeter, so it doesn't make any difference. So this is easy. Now, the next thing, next approximation is the following. If I assume that the difference between those distances, is much smaller than the coherence length, well, which is what? Well, it is c divided by delta nu. So this is the light velocity, and this is the period of the beat phenomenon, which is also equal to lambda square over delta lambda. So if I assume this, what I can do is to say that, well, these two amplitudes are the same because the amplitude varies, well, as a function of the distance, with the wavelength, which is the coherence length. So if the difference in distance is much smaller, I can say that, well, this is the same as this one. So here I put number 1. Because here maybe the amplitude is that, and just a little bit farther, it's still there, and it decreases very slowly, You see? So this is the approximation I make. Then I can do that. Now what I do, I just say, okay. Okay. I can do that, as long as the difference between the distances from source element I to hole 1 or 2, is much smaller than the coherence length, So this is the significance of the coherence length. So in the experiment of Michelson, you have to make sure that the difference between the distances coming from a distant source, to the focal plane, is less than the coherence length, either going through the hole 1 or going through the hole 2. Okay, so this is what I'm getting. And now what I should still do is to take the time average, and to sum over all the source elements, Okay, so now, here I forgot something, You agree that I'd written this, but I forgot to write the other one. I2P nu T, and now minus R I2 over C. This I'd forgotten, because when I wrote, this contribution, so I made use of this, well, of the first part, it was okay, of this, and now for the second one, I made use of that, but I should also make use of that, Now, when I see that the temporal time contribution goes away because of the minus, but there remains something, So when I make the product of the two, what I find is that exponentiation of minus 2 pi nu multiplied by R I2 minus R I1 over C. Now here, it's a question to you. Do I have the right to replace here the number 1 by the number 2 or not? Why? The reason is that now the frequency here is not delta nu. It's not this low time dependence or space dependence. Yeah, it's something of the order of lambda, the wavelengths. Yeah, which is short. Yeah, so this quantity varies very much. Yeah, as a function of the wavelengths. Yeah, so here I have no right to do that. Yeah. Okay. So what do I do next? I just show you where we are. So this is essentially this quantity and this one, with the condition that I made the assumption that the difference between the two distances here is smaller than the coherence length. Now, the quantity I represent here, so the square of the module of the real amplitude of the electric field by the surface element I, yeah, I can represent it as being equal to what? Where the intensity at that location, yeah, multiplied by the surface element. Okay? So you agree, yeah? The square of an amplitude is an intensity, but I have to take into account the size of the source element I'm considering, which is infinitesimal, yeah? But I have to take it into account, yeah? And now, after I make what? I make the time average. So I take the time average with before a summation. So let's start again. First, I make the summation on I from 1 to n. And after I take the time average, so here I make summation on I from 1 to n. Then I take the time average. What do I find? Well, I find the following. I find that it is equal. I replace the summation I by an integration over the surface. Yeah, so it's a double integral. Yeah, if you want, it's I S ds. So I've taken into account this. Now I have to divide by the square of the distance, yeah, of the source element. So this is taking into account this effect. So all of this I've taken into account. And now I should still include that one, times the exponentiation complex of minus I2 pi nu times Ri2 minus Ri1 divided by C. Okay, so this is what the complex degree of mutual coherence is equal to. So it's equal to integration over the surface of the source, yeah, of its intensity divided by the geometrical dilution effect and corrected for this factor. And this is what we have established now is known as the van Cittert-Zernike theorem. Okay. So this is the Zernike-van Cittert theorem. Now, in all of that, yeah, I forgot one thing. Yeah? You see here, I have divided by I. Here I have divided by I. Here I have forgotten to divide by I. So I correct for this, I divide by I. And here, I also divide by I, where I is the intensity of the source. Yeah, yeah, the integrated intensity of the source. Okay, this is already a very interesting result, yeah, but which can still be simplified, yeah, due to several obvious assumptions, yeah. So in what follows, yeah, we will assume that where the source is an extension, so an extension which is small compared to the distance between the source and the observer. So this is a very good assumption, yeah. And also that the distance between the 2 points which is part of my interferometer, yeah? So the distance, the baseline, is small compared to the distance between the source and the observer, yeah? So double assumption, yeah, but which is obvious. This is known as the Fraunhofer approximation, yeah? So I assume that the extent of the source and that the distance between the two elements of my interferometers, yeah, is small compared to the distance, yeah? Well, here typically, yeah, we have at maximum 400 meters, yeah? And here typically, yeah, you have 100 of light years, yeah? So good approximation. And also about the extent of the source, yeah? So we shall make use of those two assumptions, yeah, to simplify, yeah, the Zernike-van Cittert theorem. By this expression too, well, integration over the surface of the source divided by I of the exponentiation of minus I2 nu multiplied by R I2 minus R I1 divided by C. I1. Okay. Okay. So this is a diagram, yeah, showing you the source, which is very distant, yeah. And I represented a source element with a surface dsi. And the point pi, yeah, is coordinates x prime, y prime, z prime. Now, my system of coordinates, yeah, is centered on one of the elements of my interferometer, in this case P2. Well, it's not important. This is Cartesian coordinate 0, 0, 0. X goes in that direction, y goes in that direction, and z goes in that direction. And what we are assuming, yeah, is that the distance z prime, so the distance between this element and the source, is much bigger than the module of x prime, y prime, module of x, or module of y. So the distance between the two elements of my interferometer or the extent of the source. That's all, yeah? Okay, now let's evaluate, yeah, what is R2 minus R1. And this is something very similar to what we've done yesterday, yeah? So, well, let's calculate, yeah, the module of the difference between P2 pi minus P1 pi. Yeah. So we find the following, that it is equal to the module of, so P2 pi, it's easy, yeah? P2 pi is just the square root of x prime square plus y prime square plus z prime square. Minus the square root of P1 pi. So P1 pi will be x minus x prime square plus y minus y prime square plus z prime square. So we assume, of course, that the two elements of the interferometers, yeah, is in the plane xy, yeah, for z equals 0. Okay. So as last time, what we do then, yeah, we just put this z prime square, yeah, in evidence, so it will be z prime multiplied by the square root of 1 plus x prime square plus y prime square divided by z prime square, like this, minus, so I can do like that, square root of 1 plus x minus x prime square plus y minus y prime square divided by z prime square. Yeah. Now I make use, yeah, of the Taylor development in series, yeah, of the square root of 1 plus epsilon. Yeah. So it will be 1 plus x prime square plus y prime square divided by 2 z prime square Then after will be -1, then minus x minus x prime square plus, so here will be also minus y minus y prime square divided by 2z prime square, like that, if I didn't make a mistake. So the 1 plus 1 minus 1 goes away. Now the z prime here goes away with the z prime square here. Now, when I will raise this at the power 2, the x prime square or the x prime square will go away. So what will remain is just equal to minus x square plus y square like this divided by 2z prime, and after plus the double products, yeah? So it will be plus 2, so it will be x times x prime plus y times y prime divided by z prime, yeah? If I didn't make a mistake, yeah? Okay. Now we will define, yeah, angular coordinates. So the angular coordinates are zeta equal x prime divided by z prime and eta equal to y prime divided by z prime. So what do they represent physically? Yeah? So if you divide x prime, so x is along that direction, so x prime by z prime, yeah, is a tangent of the angle under which you see that source element, yeah? Okay? So it's really an angular coordinates expressed in radians, yeah? It's the same for the other angular coordinates. So here, I find that it will be equal to minus, well, I could say, okay, x squared plus y squared divided by 2z prime. So plus x times zeta plus y times eta, right? In such a way that this expression here, so gamma 1, 2 for tau equal to 0 will be equal to what? Well, now I put a double integral because I shall integrate, yeah, over the special coordinates or angular coordinates. Yeah? So how I will do is, okay, it's the intensity, which depends on zeta, eta, multiplied by the exponentiation of minus 2 pi mu, multiplied by, well, divided by c, of course. Now c over nu, it's lambda. Yeah. So here, the c over nu, I can replace it by 2 pi over lambda. Now here, I may write x times zeta plus y times eta, correct? Yes. Then I close my parentheses. And now, in fact, what I should write here, yeah, is time dx prime times dy prime, and then divided by the distance, yeah? And the distance, well, I think I forgot it here, right? I forgot it here, yeah? So here it was a r square, yeah? Something like that. Well, which in this case, r square becomes divided by z prime and by z prime, yeah? Yeah, because it's the distance. But now dx prime over z prime is d zeta. So this is just d zeta. And dy prime divided by z prime is d eta. Now, I still have to divide this by I, and it's not finished. I forgot to write down this factor, which does not depend on the angular coordinates. Yeah? So multiply by exponentiation of I think I call it I phi xy, something like that, yeah, where phi xy is equal to what? Well, it's equal to, just a moment, it will be, well, minus 2 pi times nu over c, so over lambda, multiplied by x squared plus y squared divided by 2z prime, something like that, yeah? Okay? But this is just a term which does not depend on the source, yeah? It just depends on the two elements of the interferometer. So let's see whether we did a mistake or not. Okay, here I can put plus or minus, yeah? Plus or minus doesn't matter. Then a double integration of the intensity times exponentiation of minus I2 pi, yeah, zeta x theta, and divided by lambda, then zeta d eta, it's correct. And now here, well, the difference in the note is that I've defined now a normalized intensity, I zeta eta, as being equal to I zeta eta divided by high, and high is equal to simply I zeta eta d zeta d eta. Yeah. So this is normalized intensity. Yeah. So when you integrate, yes, this intensity over the source, you find it's equal to 1. Okay. And this is why, so you obtain the same expression but with I prime. Yeah. So the final result, yeah, is the following: is that the complex degree of mutual coherence, gamma 1, 2, which depends on which parameter, yeah? Oh, this is interesting. I will isolate, yeah, here, x over lambda. So here I write x over lambda. Here, the lambda y over lambda. Therefore, here I have the right to put x over lambda, y over lambda. Now, tau equals 0 is equal to what? A double integration of I prime times exponentiation of minus I2 pi multiplied by zeta, oops, times x over lambda plus eta y over lambda d zeta d eta. I see, and now multiply, yeah, still by the other quantity exponential plus or minus I phi xy. Now, what is nice is that, you know, the visibility of the fringes is equal to the module of the complex degree of mutual coherence. If I take the module of that, this goes away. And what I see is that, wow, the module of the complex degree of mutual coherence is equal to the Fourier transform of the distribution of a normalized intensity at the surface of the source. Yeah, and this is a fantastic result, of course. Yeah, yeah. So you see here what is, well, I even think that this is the origin of the Fourier transform. Yeah, so it comes from optics. Yeah, from the von Cittert-Zernike theorem. Yeah, but which was found independently, yeah, by Fourier, and well, we see that there is a big potential of applications here, yeah? So let's just remember that, okay, the visibility is a module of this quantity, of the complex degree of mutual coherence. So it is a module of that quantity, or which is just a Fourier transform in 2 dimensions, yeah, of the distribution of the normalized intensity at the surface of the source. Coherence. You see, it depends on the parameter x over lambda and y over lambda, yeah? So x over lambda and y over lambda. Now, I would like to find out with you what is the physical meaning of x over lambda and y over lambda, yeah? Okay. You agree if I tell you, well, t, yeah, is a period, yeah, of oscillation. The inverse of t, 1 over t, is a frequency, right? Is a frequency. Now, if I take lambda over x, you agree? We've seen, yeah, that following Evry disk, yeah, following well the piezo interferometer, we've seen that lambda over b is angular resolution of our interferometer, where b is the baseline. Yeah, so here it's the same. This is angular resolution, yeah, where lambda is the wavelength and x is the baseline. X is the distance, yeah, between two elements along the x direction. Yeah. Well, lambda over y is, of course, angular resolution, yeah, along the y direction. Yeah. Now, if I take 1 over lambda over x, well, this is equal to x over lambda. Yeah. But taking the inverse of that is taking a frequency. And because this is an angular coordinate, this is what? It's a space frequency. So it's an angular space frequency. And well, people have taken the habit of calling this, the space frequency x, as being x over lambda, and v, the y over lambda. So these are space, well, angular space frequencies, yeah? But in the literature, they don't call them angular space frequencies, they call them space frequencies, yeah? But remember, why frequencies? It's because lambda over x is an angle, is angular resolution, yeah, of your instrument, yeah? So if you take the inverse, it's a frequency. So angular space frequencies. And they are named, well, the UV coordinates and where UV plane comes from, yeah, the UV plane, yeah. So, okay, so let's rewrite all of that. Gamma 1, 2 of this angular space frequencies UV as a function of 0 is equal to, well, the exponentiation of plus or minus I phi xy multiplied by the Fourier transform of the normalized distribution of the intensity at the surface of the source, of which I'm taking the Fourier transform. So it's zeta u plus eta v, like this, d zeta d eta. Yeah? Now, what is obvious, yeah, is that what you are going to do, yeah, you are going to take measurements, yeah, of the module of that quantity, of course, yeah. So if you take the module of that quantity, this goes away. You take the module of that quantity. Now let's concentrate, yeah, just on the Fourier transform, yeah. Well, would you agree that what you would like to recover, yeah? So it's I prime as a function of zeta eta with a superangular resolution given by that of your interferometer, yeah? So what you will do, yeah? Well, you will just try to take a very good sampling of the UV plane, measuring the visibility of the fringes, and after, if you take the inverse Fourier transform of that quantity, yeah, you should recover the distribution intensity of the source with an angular resolution that would be given by a single dish, which diameter is along this baseline, yeah, along, well, the direction of interest. Now you would like to do that, yeah, for many different directions, many different baselines, so it means many different space frequencies, yeah. And for that you will take advantage of the Earth's rotation, of course, and by moving one element of the interferometer with the other, yeah. Then you will make what is known as aperture synthesis, yeah, aperture synthesis, yeah. Now the problem with the telescope, optical telescopes, is that you have very few elements. Yeah, I think the Schara Shara array has 6 elements, yeah, which is already nice, yeah, because when you use 6 telescopes, yeah, you may at one time, yeah, get 15 frequencies, yeah, right? So it's a C62 number of combination, yeah, of 6 elements taken 2 by 2. With the VLT, yeah, you only get 6 at a time. But with the Earth rotation, yeah, well, you may succeed, yeah, in covering rather well the plane. And then, well, at the VLTI, they have auxiliary telescopes, 4 small auxiliary telescopes, which can be moved, yeah, moved along rails. And this goes very fast. So during the night, yeah, you may take many different configurations, which is nice, yeah. So just as a reminder, we could say, okay, I prime zeta eta is the inverse Fourier transform of that, yeah? So we'll say, okay, it's equal to the double integration of, well, in principle, we should reinsert here this quantity multiplied by gamma 1, 2 u v0 times exponentiation of inverse Fourier transform. Now the minus sign has disappeared. Zeta u plus v eta, and now du d eta. Yeah, so this is the magic, yeah, of the interferometry by taking the inverse Fourier transform. Yeah, if you make a large number of measurements, yeah, of the complex degree of mutual coherence, it means, you know, visibilities for different configuration of your telescopes. You pave very well, yeah, the UV plane, and by taking the inverse Fourier transform, you recover, you make aperture synthesis imaging, yeah, with an interferometer, yeah. Yeah. Okay, now we have time, yeah, still to make maybe few applications. Okay. Yeah, I've said all of that. So, well, let's first remind, yeah, some properties of the Fourier transform, yeah. And so I just remind you that in one dimension, yeah, the Fourier transform of the function f of x, yeah, is integration from minus infinity to plus infinity times exponentiation of minus 2i pi times sx dx, yeah. And this is a nice formulation of the Fourier transform, because when you take the inverse Fourier transform, well, the coefficient you have just before the integration, yeah, is always 1, yeah. Otherwise, sometimes 1 over square root of 2 pi, complications which are unnecessary. Yeah? So this is a one-dimension Fourier transform. Now I just say the functions, yeah, the original function and its Fourier transform form a Fourier pair. Now, the Fourier transform of that function exists if the function fx, yeah, is bounded, summable, and has a finite number of extrema and or discontinuities. Yeah. Now, this does not necessarily mean that the inverse Fourier transform, yeah, denoted ft minus 1 of ftf, yeah, will give you f. Yeah. Well, for it to happen, yeah, what you need is that the following integrals, yeah, must exist. Yeah. So if it's not bounded, yeah, then you cannot recover the inverse Fourier transform. But well, this is usually the case. Yeah. So the inverse Fourier transform, yeah, is just the Fourier transform times this. Yeah. That's what we have seen there. Yeah. These are just reminders. Yeah. Now we can of course generalize the Fourier transform to several dimensions. So n dimensions. Yeah. So the Fourier transform, yeah, of a function which depends on a vector, yeah, w, is just this, yeah, where here you have the scalar product, yeah, of the vector w by the vector r. And it's what we've seen here. We already here have a Fourier transform in a two-dimensional space, yeah, but you can generalize it to any number of dimensions. Okay, now this is just a reminder, yeah. If a function ft designates a function of time, yeah, its Fourier transform, yeah, well, as a content of a function of time frequencies. Yeah, this we know. So similarly, yeah, well, it's what we have seen here. If the function f, yeah, here it was the intensity, is defined, yeah, on a two-dimensional space, then this function represents the special frequency content of the function f. Yeah, so it's what we have seen, yeah, in terms of the UV frequencies. Now, among the interesting properties that we shall make use, yeah, very often in the exercise, yeah, are the following for the linearity properties. So if a is a constant, a real constant, the Fourier transform of a function f multiplied by a is just a, the constant a multiplied by the Fourier transform of f. This is obvious, yeah? Now the Fourier transform of the summation of two functions, well, it's just the summation of the their Fourier transform, yeah? This is obvious too. When it will not be so obvious, yeah, I will make the demonstration, yeah? Now about symmetry and parity properties, yeah? Well, I don't make use of those, yeah? So I will just skip, yeah, and go to the essential. Okay. Oops. Oh, this is a nice property because, well, we will make use of it, yeah, in a, well, very often, yeah? So I will just demonstrate this one, yeah? So, well, it's good to refresh our memory, and so let's make this exercise, yeah? So let's take the Fourier transform of a function f, which depends on the variable x divided by the real constant a. And the Fourier transform, yeah, is a function of s, yeah? So do you agree that this is equivalent to write that it's integration from minus infinity to plus infinity of the function f of x divided by a times exponentiation minus 2 pi x times s dx. So this is the definition. Yeah? So if there is any difficulty, yeah, just let me know. So let's make the change of variable y equal x over a, which implies that dx is equal to a times dy. So we find that the Fourier transform will be equal to integration. If a is positive, the integration limits will still be from minus infinity to plus infinity. If a is negative, yeah, it will be the reverse. It would be from plus infinity to minus infinity, yeah? So I will make the demonstration assuming that a is a real positive, okay? So in that case, it's from minus infinity to plus infinity of the function f of y times the exponentiation of minus 2 pi. Now x is equal to a times y. So I write here y times a times s. Now dx, it's dy times a. So this is equal to a times this quantity. But this quantity, you agree, is a Fourier transform of the function f of x, but not anymore for the variable s, but for the variable a times s. Okay? And this is, well, what is the result there, yeah? So it's a similarity, yeah, property, that the Fourier transform of function x divided by a is equal to a times the Fourier transform of fx, but evaluated for the product of a by s. Now, if you make it the case a negative, what you find simply is that you have to put the module. Okay, interesting. Now, okay, the meaning of that is that the dilation of a function causes a contraction of its Fourier transform, yeah? Indeed, yeah, if a goes to 0, yeah, well, or okay, well, if a goes to 0, this goes to 0, but here you know it goes to infinity, yeah? So it means that the Fourier transform, for instance, of a direct function will have a very wide content in space frequencies, and vice versa. If you have a very spread function, its content in frequencies will be very narrow here. Okay. Now, this is another very interesting property, the translation property. Yeah? So, what about the translation property? So, let's make the demonstration. So, let's evaluate the Fourier transform of a function f which depends on x minus a, and here variable s. So, by definition, this is the integration from minus infinity to plus infinity of fx minus a times exponentiation of minus 2 pi xs dx. You agree? This is the definition. Change of variable as before, y equal x minus a, which means that dy equal dx, and also that x will be equal to a plus y. So the Fourier transform becomes integration from minus infinity to plus infinity of f of y, this is good, times exponentiation of minus 2 pi s times x, so times y, times dx dy. But now I still have an exponentiation of minus I2 pi as, like that. Now, this is simply equal to exponentiation of minus I2 pi as multiplied by the Fourier transform of the function f of x, well, which depends on the variable s. Yeah. So, and now, so meaning of that is that the translation of the function in its original space, yeah, this is a translation, corresponds to a phase rotation of its Fourier transform in the transform space. Yeah. Oh, now it's good. The door function, yeah. So the door function, yeah, because it will be very often used also. So the door function, yeah, so this is x with 0. Now here I have x equals 0.5, x equals minus 0.5, and the door function is defined as follows. It is 0 if the module, yeah, of x is bigger than 0.5, and it is equal to 1. 1, you're 0, yeah, if it's less. Now, let's evaluate what is the Fourier transform of the door function. Well, it's easy. It's the integration from minus infinity to plus infinity, but okay, I will just write it, of this function times x dx. So I replace this function, yeah, by the boundary, so it will be from minus 1/2 to plus 1/2 of exponentiation of minus I2 pi xs dx. Now change of variable as usually. So let y equal to minus y2 pi xs, which means that dx is equal to dy divided by minus I to pi s, like that. So the Fourier transform becomes equal to, okay, when we have a minus 1/2 here, it will go to I pi s. Here it will go to minus I pi s of the exponentiation of y times dx, which is dy divided by minus I 2 pi times s. So now it's very easy to integrate this exponential function. So it's just equal to, and we have a sign minus here, yeah? So it will be exponentiation of I pi s minus exponentiation of minus I pi s divided by 2I pi s. Now, this is easy, yeah? It will be 2 times I times the sine of pi s, yeah? So the 2I will simplify with those, and what will remain is the sine of pi s divided by pi s. Yes? Yeah. So the original function, so this is the sine cardinal function, yeah? This is the result, yeah? The Fourier transform of the Dor function, yeah, is just a sine cardinal, yeah? Now, what is amazing, yeah, in optical interferometry, yeah, it's very useful to work with square apertures or rectangular apertures because you are always using Dor functions or window functions, yeah? Well, in theory, you would prefer, yeah, to use circular apertures, yeah, yeah. And well, technically, yeah, this is more difficult, yeah. Not so much, but well, for a theoretical physicist, not difficult, yeah. For an astronomer, yeah, well, it's a bit cumbersome, yeah. And now, what happens is that, okay, you can do all the theory, yeah, with square or rectangular apertures, yeah. You'll get the very deep inside of interferometry. Now, if you want to be more rigorous, you use circular apertures, and what you will find is that the cardinal sign will become a Bessel function of first order Bessel function. That's all. So it's interesting, yeah, during this long break until Monday, that you go back, yeah, in your textbook, yeah, and see, yeah, well, what's the definition of a first order Bessel function, because next time when we meet, yeah, we'll make use of it, yeah. So because we don't want to be despised by theoretical physicists, yeah, yeah, and to show them that we also know how to handle those, yeah. Now something I would like to propose as an exercise for the next lecture to you is the following. So, well, we've seen this nice theory about the Fourier transform. Let's assume the following, yeah. I will make it very simple, yeah. That you observe in the sky, in 2 dimensions, a star, which is square, yeah. So I make things simple, yeah. Next time I'll make circular, but now square, yeah. And well, I assume that the angular size of the star, yeah, is zeta 0, and also along eta is also zeta 0. So it's a square star, yeah. Now I would like to ask you, yeah, to calculate for next time, yeah, what is the visibility of such a star if I use an interferometer with 2 elements, yeah, separated by a baseline B, yeah, and to show me, yeah, what is the result, yeah, of observing a square star. So you have everything. We know that, okay, the visibility will be the module of the complex degree of mutual coherence, which is a module of the Fourier transform of that quantity. So what you should find out, yeah, well, we know that the angle zeta goes from minus zeta 0 half to plus 0 half. eta goes from minus zeta 0 half plus zeta 0 half. I0, I prime, what is I prime? Well, it's a constant because it's uniformly bright. The star is uniformly bright, yeah? But it should be normalized in such a way that when you integrate your intensity over those coordinates, you find 1. And then you will find, what is the visibility, of observing a square star in the sky with an interferometer, So next time, I will ask, well, one of you, if you agree, to come and show your results,